Lecture 10. Today we're going to be covering pendulums and the small angle approximation. Today's lecture is going to be a bit different from the norm. We're not going to do any example problems, and really what we're going to do is we're going to focus on this one system, the pendulum, and we're going to go into quite some depth in it. We're going to use calculus, and so if you're not familiar with that, then feel free to skip this lecture or skip the parts where we use calculus to derive the pendulum's motion. But yeah, this is going to be less of a basic skills kind of lecture and more of an investigation. So let's get started by defining the small angle approximation. Any function that's infinitely differentiable, a function for which we can take its derivatives over and over again, can be written as what we call a Taylor series. So a Taylor series is a polynomial in terms of the function's argument that as you add more and more terms, it gets closer and closer to the actual function. So for example, for sine of x, the polynomial starts x minus x cubed over 6 plus x to the 5th over 120, etc. There are more and more terms, and the more terms you add, the closer you get to sine of x. For cosine of x, it's 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720, etc. And so, you can take these series out to any number of terms, hundreds, thousands of terms, and you'll get closer and closer approximations to the actual functions, which are, defined in terms of right triangles. And actually, calculators use Taylor series to approximate a lot of these functions. But what we do with the small angle approximation is we assume that the angle is very small. So as you can see down here, we're using this less than sign. That means that theta, the angle, is much less than pi over 2. And so what this lets us do is that, recall that, let's say we have a polynomial x to the n, a function x to the n. As n increases, gets greater than 1, the value of x to the n between 0 and 1 becomes less and less. And so what we can do is we can, for values of theta that are very small, we can neglect these higher order terms entirely. So the Taylor series for cosine of x, for example, 1 minus theta squared over 2 plus theta to the 4th over 24 minus theta to the 6th over 720, we can neglect the theta to the 4th and theta to the 6th terms when the angles are small, because theta to the 4th and theta to the 6th are so small that they might as well be 0. And that's what it means to do the small angle approximation. Now there are two ways we can implement the small angle approximation. One way is we can cut off all the terms where the exponent is greater than 2. So that means that we approximate sine of theta as theta, cosine of theta as 1 minus theta squared over 2, and tangent of theta as theta. Or we can cut off all the terms where the exponent of theta is greater than 1. Which means that cosine, instead of being 1 minus theta squared over 2, is just 1. And we're going to use the latter approximation because it's simpler, the math is simpler, and we don't really lose that much exactness, and it kind of allows me to make an easier case for why the pendulum is a simple harmonic oscillator, as we discussed last lecture. Anyways, let's move on to the definition of the pendulum system. So a pendulum can come in many shapes, but we're going to deal with a very simplified version, which is basically a point mass, a bob of mass m that has 0 volume. It's just a point. So a bob of mass m that hangs from a rigid, massless, infinitely thin rod of length L that rotates around a frictionless pivot. So the only forces in this system would be the force of gravity acting on the bob and the force of tension that the rod exerts on the bob. So there's no friction of any sort as the pendulum rotates, and there are no forces on the pivot or on the rod, because if there were, they would accelerate infinitely. And we define an angle theta between the rod and the vertical axis. So if the rod is hanging straight down, then theta is 0, and if the rod is pointing all the way out to the right, then there's an angle of pi over 2. And we assume that the small angle approximation is valid and that we can cut off all terms in the Taylor expansion after the theta term. So sine of theta is approximately equal to theta, cosine of theta approximately equal to 1, and tangent of theta approximately equal to theta. And yeah, let me do a drawing to show you what I mean exactly. We are going to use black. Here is our pivot. Let's make this rod. Yeah, that's fine actually. Here's the rod, and here's our bob. I've drawn the bob as a circle just for simplicity. In reality, we're assuming that the bob has a negligible size. And let's use blue for this geometry. Here's our angle theta. So now what I'm going to do is I'm going to draw a free body diagram, and I encourage you to pause the video, draw your own free body diagram for the system, and then come back so we can walk through the process together and you can check your answer. Alright, hopefully by this point you've drawn your own free body diagram. So I'm going to use this green to draw forces. Let's start off with the force of gravity because we know its magnitude. It has a magnitude of mg. And next off, we know that so we can break down this force of gravity into components that are parallel to the rod and perpendicular to the rod. So let me do this here. Here's the parallel. Let's make this a straight line. The parallel component, that's good enough, and the perpendicular component. Yeah, I'm drawing this on a laptop, so it is a bit difficult, but I can mostly see that it's working out. And let's use our initial color blue to label the angles. Notice that this is theta again, because gravity points straight down, and this points in the same direction as the rod. And because this is a right angle, I don't know if you can see my mouse, but yeah, this is a right angle. So this has to be pi over 2, pi over 2 minus theta. And so what we get for the magnitude of these two forces is this would be mg cosine theta, and this is mg sine theta. Come on. mg sine theta. Let's make this a bit wider. Come on. Sorry. Alright, whatever. That's fine. mg sine theta. There we go. Sorry about that. Alright, so the only force left is tension, which we know is parallel to the rod. And we know that our bob here can't accelerate in the direction of the rod, can't accelerate parallel to the rod, because if it did, then our rigid rod would be stretched, and that's something we cannot have. So tension is going to cancel out the force of gravity here that is parallel to the rod, so that our bob here doesn't accelerate in the direction of the rod. And so there's tension. It is equal and opposite to the force of gravity here, so we have tension is equal to mg cosine theta. So the net force on our bob, which I'm going to indicate with this lovely magenta, is mg sine theta. And now what I'm going to do is I'm going to break mg sine theta, this net force, down into components for us. And I'm going to use the same components color as I did earlier. No, I'm going to use this dark blue for components. So we have this. And, well, actually, let's try and simplify this diagram. I'm going to delete this, delete this, delete this, or here. Let's delete all this. Okay, that's better. So now we have the components here, which are parallel to the y-axis and parallel to the x-axis respectively. And okay, notice that this angle is theta, and this angle is pi over 2 minus theta. So the magnitude of this force is, bear with me here please, this is mg sine theta cosine theta, and this here is mg sine theta sine theta. And there we go, we made it wider. So that's the magnitude of the force on our pendulum. It is negative mg sine theta cosine theta in the x direction, and negative mg sine theta in the y direction. And the reason for the negative signs is that this force is pointing left, while x traditionally points right, and this force is pointing down, while y traditionally points up. And when I say x and y, I mean the I hat and j hat unit vectors, if you want to think about this in terms of vectors. Alright, but that's our net force on the pendulum. So now let's do our derivation. First, let's describe, so we're going to use vectors here to make the math simpler. First, let's describe the position of our bob here in terms of the angle theta as a vector. So notice that if theta were to be 0, the position would all be y, would all be in the negative j hat direction, and none of it would be in the I hat direction. That implies that, well, here, if you look at it like a right triangle, then we can see that position is proportional to negative cosine theta, and y position is proportional to negative cosine theta, and x position is proportional to sine theta. And yeah, actually, I think you can go ahead and do this intuition on your own. But it's pretty easy to see why these directions are the way they are. So using our small angle approximation, I hat times L sine theta minus J hat times L cosine theta is approximately equal to I hat L theta minus J hat L. And then our acceleration, which is the net force on the bob divided by its mass, is negative I hat G sine theta cosine theta minus J hat G sine squared theta, which is approximately equal to negative I hat G theta. Notice that I didn't include the theta squared term from the J hat G sine squared theta term of the force. That's because we're cutting off everything as the theta squared term. So don't think that, okay, sine theta is theta, so sine theta squared is theta squared. No, because we're cutting everything off of theta squared, we're approximating cosine to be 1, not 1 minus theta squared over 2. Then sine of theta might be theta, but sine squared of theta is 0. So that's important to recognize when using the small angle approximation. Alright, we're going to get calculus back in here. The second derivative of r, which is acceleration, and notice that I used vectors earlier, but I dropped the vectors here because the second derivative of r is only in the I hat direction, and a is only in the I hat direction, so we're just dealing with the magnitudes here. So the second derivative of r is L times the second derivative of theta, which is equal to the acceleration, which is equal to negative g theta. So you have that the second derivative of theta is equal to negative g over L times theta. And we can solve this differential equation, if you remember, by noting that the derivative of sine of theta, sine of, let's say, omega times theta, is omega times cosine of omega theta. Omega times cosine omega theta. And the derivative of omega cosine omega theta is negative omega squared sine omega theta. So that's the way to solve any of these differential equations that set some, let's say, x double prime equal to negative x. The solution is always a sum of sine and cosines, or equivalently a sine with a phase factor. So our solution here in most general form is theta equals a, the amplitude times the sine of omega t plus phi, where omega is the square root of g over L. So omega is again our angular frequency, and phi is our phase factor that just describes the initial state of the system, the state at time equals 0. You can equivalently write this in terms of a sum of sine and cosine functions with the same frequency, but personally I find that to be clunky, and I like how you get the amplitude straight out like this. Obviously you have to solve given the actual initial numerical conditions of the problem, but that's perfectly fine, and we're not dealing with specifics here, just with the general pendulum system. So yeah, notice that this is the exact same as the simple harmonic oscillator formula I showed you last time. That's because Hooke's law actually gives a very similar equation. It gives us that x double prime, the acceleration of the mass at the end of the spring, is equal to negative k over m times x, because force is negative kx, so acceleration is negative k over m times x. So instead of having the variable that's oscillating be theta, we have it as x in a spring system, and the frequency, instead of being the square root of g over L, is the square root of k over m. So there's a lot of similar parallels, and in general, anytime you're able to find some kind of equation like this that sets the second derivative of some quantity equal to the negative of itself times some constant factor, that's a simple harmonic oscillator right there. And so many systems can be approximated nicely as simple harmonic oscillators, and it's a really key tenet of classical physics and a key skill to have, approximation as a simple harmonic oscillator. So yeah, thank you for bearing with this complex lecture today. I hope you enjoyed shedding some insight on the pendulum and doing this heavy lifting. I feel like the payoff is pretty good. But yeah, thank you for watching, and see you next time.